Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this example, we're going to compare two different circuits, which look just like this circuit we have here, where we're moving a metal bar along these wires here and inducing an EMF in our bar and causing current to flow in this circuit. But the only thing we're going to change between the circuits is the resistance, and we're going to look at the ratio of the EMFs given that we have different resistances. So imagine two circuits just like this, where one has a resistance of 55 ohms and the other has a resistance of 110 ohms, or um, the resistance of one is equal to the resistance of 2 over 2, right? R2 is twice that of R1. Okay, so first if we look at the ratio of the EMF in circuit 1 versus the EMF in circuit 2, well, let's consider how we would calculate the EMF. Since we have a metal bar moving in a constant magnetic field, and the velocity of the bar, the length of the bar, and the magnetic field are all perpendicular to each other, we know that the induced EMF is just going to be equal to the velocity of the bar times the magnitude of the magnetic field times the length of the bar. So if you notice, none of these actually depend on the resistance in our circuit. So the induced EMF is totally independent of our circuit. So this ratio should just be VBL over VBL, which is 1. All right. Now, let's look at the ratio of the currents in our two different circuits. Now, the current is going to be dependent on our circuit configuration. So this one should not be 1. Okay, so if you recall from Ohm's law, we know that the voltage in our circuit is equal to the current in our circuit times the net resistance. And if we rearrange this for I, we'll have I is equal to V over R, where the voltage, in this case for our circuit, is going to be created by or is going to be our motional EMF, right? We're creating the voltage by moving our bar in a magnetic field. So we can just replace V with our EMF, since that's acting as our battery. So we can replace, in our equation here, each current with E over their respective resistance. So I1 over I2 is going to be equal to E over R1. Remember, E is the same for both circuits, divided by E over R2. So the E's will cancel out, the epsilons. And then we could plug in numbers for our resistances, or we could substitute for this relationship here. R1 is R2 over 2, or the same thing is 2 times R1 is R2. Those are the same equation. So if I put 2 times, or first let's simplify our equation here, right? We have a 1 over R1 divided by a 1 over R2. So we'll flip over that 1 over R2 up to the top, and we'll have an R2 over R1. And now we'll substitute our R2 for twice R1. So we'll have twice R1 divided by R1 will just give us 2. So let's see what this means and if it makes sense. So I1 is the circuit with a smaller resistance. So therefore, it's going to have twice as large of a current, which makes sense to me since the EMFs are the same for both circuits. All right. Now let's make things even more interesting. Let's imagine that the rod in our first circuit is moving at twice the speed of that in the second circuit. So the velocity of the first rod is equal to twice that of the second rod. And we want to figure out what the power dissipation is through our resistor in each circuit. But specifically, we want to look at the ratio of the powers again. So just like we've been doing, looking at a bunch of different ratios here. So it's going to help us if we remember that the power is just equal to the current in our circuit times the voltage, or sorry, the current going through our resistor times the voltage drop across that resistor, which for us is just going to be I times V, or I times the EMF, since that's acting as our voltage. And the EMF, or the current, is going to be unique to that circuit, right? And before we were saying the EMF was also was something that was not going to be unique. It was going to be the same for both circuits. But now in this situation, since we have different speeds of the moving bar, the EMF will actually change. And we're going to show that that's true. So let's look at our expression for the EMF again, VBL. We can see that B and L will stay the same, right? But this V is going to change, right? So we'll have a V1 and a V2. So let's go ahead and start substituting in to our equation here. We also know that the new currents here, I1 and I2, should also change, right? Because above we said that the current is just equal to epsilon over R. And of course our epsilon changed. So we'll have a 1 here, a 1 here, and a 1 here. These will all be subscripted. Okay. So let's go ahead and substitute in for the current first, because we'll have everything in terms of epsilons and R's. So if I do that, I will have epsilon 1 over R1 times epsilon 1. And on the bottom, we'll have E2 over R2 times E2. Or we'll just get EMF1 squared over R1 divided by EMF2 squared divided by R2. Or if we flip the bottom over to the top, we'll have EMF1 squared times R2 over R1 times the EMF for 2 squared. All right, so now we can go ahead and plug in for our EMF here with V1 times B times L. If we do that, we'll have V1 squared B squared times L squared times R2 in the top. And in the bottom, we'll have R1 times V2 squared times B squared times L squared. So we can see that the B's and the L's will cancel each other out. And we'll just be left with R2 over R1 times V1 squared over V2 squared. Okay. So now we know that R2 over R1 is 2, right? Because the resistance in the second circuit is twice as great as that in the first. So this will be 2 times V1 over V2 squared. And V1 over V2 is going to be equal to 2, right? If I just divide this by V2, this equation here, top and bottom, V1 over V2 is equal to 2. So if we square that, we'll get a 4, and 4 times 2 is equal to 8. So the ratio of the power dissipation in each circuit through our resistor is going to be 8. So circuit 1 dissipates 8 times as much power as circuit 2.